So in this chapter, we're going to be looking at working with vectors. We're going to start with something slightly different. We're going to look at motion using vectors, and we're going to try and focus on position vectors. We'll start off with constant velocity. Don't get this confused with a so-called SUVAC question, which is based around constant acceleration. Here, constant velocity means it's moving with the same velocity for the entire journey. So, let's say we had a ship that was moving with a velocity of 3,1. Every second, it would move 3 to the right and up by 1. So I'm going to introduce some new notation here. We'll use R to represent the new position vector, and R0 will represent the original position vector. Well, we can find the displacement of this object by taking its velocity, its constant velocity, and multiplying that by time. So if it moves 3,1 every second, after 2 seconds it would have moved 6,2. And after 10 seconds it would have moved 30,10. So we're going to use that to describe the displacement. But to get the position vector, I'm going to need the original position vector plus the displacement that's occurred from the beginning of the journey. So, if the original position vector was 2,4, when t equals 1, firstly the displacement is going to be velocity times 1, and my new position vector is going to be 2,4 plus 3,1, which gives us 5,5. So that's the displacement after 1 second. How about after 2 seconds? It's going to be the original position vector plus 2 times the velocity, since it's moved with that velocity for 2 seconds. And it follows for 3 seconds as well. In general, the new position vector is the original position vector plus the displacement. Okay, just before we move into the next section, I just want to recap and expand on some cardinal directions. Cardinal directions are compass directions: northeast, southwest, and all the ones in between. Now, the vector questions we're going to work on could ask us to refer to some of these cardinal directions. And I think the two most common ways they do refer to them are to tell you that a particle is moving in one of those directions, in which case we'll use the velocity. That's the variable that lets us know what direction our particle's moving. In 2D, a positive velocity lets us know we're moving in the positive direction, usually up, and a negative velocity lets us know we're moving in the negative direction, usually down. So it lets us know what direction we're moving. So that's velocity. But since we're working with position vectors, the question might say something like, when is the particle due east? Or when is the particle due northwest of the original position of the starting point? And there, once again, we need to make use of cardinal directions. So I'm just going to quickly show how we can generalize each of these directions. So just to reiterate, we might be talking about the way that a particle is moving, or we might be talking about the position of a particle. But all of the generalizations I'm going to be mentioning are true for both of these cases. Just the variable we apply it to, the position vector or the velocity, that is going to be the difference. Okay, so let's start with some of the more popular ones. So north and east are very popular. If I was due east, I might have a vector of 3,0, 5,0, 10,0, 18,0. In general, my vector is going to be k0, or in the form k0, meaning I can have any value for the horizontal displacement, but the vertical displacement I know will definitely be 0. Similarly, for if I'm due north, 0,4, 0,7, 0,13, generally 0k. The horizontal must be 0, and the vertical can be any value of k. Any unknown value, I should say. What about if I was actually moving northeast? What form could the vector take? So if I'm referring to northeast, the vector can take a form 3, 3, 5, 5, 18, 18. What we know for sure is that it takes the form k, k. Both the horizontal and vertical component must be the same as each other. So I might have an opportunity to equate the horizontal and vertical component to each other. But this is the general form for the northeast direction. And it should follow through and make sense for some of the other directions. Southeast, k, negative k. The vertical is just the negative version of the horizontal. It's the horizontal negated. How about if I was moving west? Well, the vertical component is still going to be 0, but we should realize that the k value is going to be negative. The horizontal component is going to be negative. Southwest, similarly, kk, but we're expecting negative values. So using this, it should make sense to get a general expression for each of these cardinal directions, so you know what form the position vector should take. Okay, so in this example, we've been told that the particle has a position vector of 3, 7, and it's moving with a constant velocity, good to see, constant velocity of 2, negative 1. So just a quick diagram, trying to get the right directions. So my initial or position vector, 3, 7, I know that I'm moving in this negative gradient for the velocity. I'll just put these little markers to try and show individual seconds of time, like I showed on the previous introduction. And there's my position vector r. So let's find this displacement. It's going to be the velocity multiplied by t, which gives us 8, negative 4. And then to find the position vector, 4 seconds later, it's going to be r0 plus ut. That's going to be 3, 7 plus the 8, negative 4, which we can easily work out as 11 and 3. Okay, I've used ut a lot. You'll see this same formula with vt. U and v are actually interchangeable. They're the same, since we're actually moving with constant velocity. The initial and the final velocity will be the same. Okay, next we want to find the time when the particle is due east of the origin. Well, we already looked at these cardinal directions and the generalizations. If it's due east, I know it's going to have the form k0. It's got horizontal displacement, but it has no vertical displacement at all. So all of these would be valid for due east, and in general, it's k0. All right, so we want to know when that position vector takes that form. First, let's get a generalized position vector, because we don't know the time, so we're going to leave in the variable t. So I can say r equals r0 plus ut, generalized ut. I'm working that out. I'm writing it as one resultant vector, 3 plus 2t, 7 minus t. Okay? And if I want the form for due east, the general form, I need the j component to equal 0. That j component must equal 0. And I hope you can see that quite quickly. That's going to leave us with t equals 7. So when the time is 7 seconds, then the particle is exactly due east of the origin. So I can succinctly say the particle is due east after 7 seconds. Okay, let's look at another type of question. As I start to read through, I see that the particle moves with constant acceleration. Right there, it's not constant velocity, constant acceleration. I know it's a SUVAT question. So I'll start with my SUVAT variables, lay them all out, and just rereading, the initial velocity is negative 3, 1, the acceleration is 2, 3, and we want to know what's its velocity after 3 seconds. So setting these all out, we realize we can use v equals u plus at, and just subbing in our vectors and doing some sensible rearranging, we get a final velocity of 310. All right, we've been asked for the speed and the bearing at that time. Let's actually just draw this vector first. So 3 to the right and 10 up. This diagonal line is the vector. And we've been asked to find its bearing So we know we're looking for the angle between a horizontal north line and the vector itself. So I'll just add in a few more measurements there. Well, we can find the magnitude of this vector by doing a spot of Pythagoras. So it's the root of 10 squared plus 3 squared. It's the root of 109. Pick up our calculators. 10.44 to 2 decimal places. And then we're at the bearing. All right, so we know we should be using the tan function in this right angle triangle. The opposite is 3. The adjacent is 10. Gives us an answer for theta. So 16.699. It's a bearing, don't forget. So I need a 3-digit, well, at least 3 digits before the decimal point. So 016.7 degrees should be good for your bearing. Diagrams are useful at every stage of the question. So even this bit about what is the magnitude and the angle, just a quick diagram ensures you get the right values for Pythagoras and you get the right values for the trig, for the tan statement that you end up writing. And obviously it helps you to really visualize the north line. So asking for the bearing was the same as asking for the angle that it made with the vector j, as long as we're going clockwise. So don't forget there's multiple ways to describe the same question or for the examiner to ask you to do the same thing. When you have a diagram in front of you, you realize you can reword the question for yourself. You're interpreting what the diagram's asking you to do. And so if the wording of the question has thrown you, you kind of have another way to approach and think your way through. Okay, let's have another look at another example. So here we've been told that there's an ice skater, and as we read through the question, we realize that we're asked to find the acceleration. So we must be working with a SUVAT question. So just setting out those variables. Initial velocity. We've also been told the velocity after 20 seconds. So obviously time we have as well, which equals 20, and we have an unknown acceleration. So a question mark, should really be a question mark here. And then we can decide on which of the equations we're going to use. So V equals U plus AT sounds good. And we'll just throw in those variables. So some smart rearranging from here. We get 20A as the subject. So 20A equals -8, 4. And then just dividing through by 20, A should give us -0.4 and -0.2. Sorry, positive 0.2. So that's the acceleration. A equals -0.4, 0.2 meters per second squared. The second part of the question says find an expression for S. So that's the displacement in terms of T. So we just want one resultant vector using the term T. So we'll substitute in our initial velocity, we'll substitute in the acceleration that we've just found. So this is what we get by substituting, but I want to write that as one resultant vector. Again, these are always more useful for us, and we'll hopefully get an opportunity to see how useful it will be. Okay, so there's my expression for the displacement. Next, we're asked to find the time it takes for the skater to be directly northeast of the origin. All right, so we looked at these cardinal directions. Northeast, if you remember, the vertical and horizontal component of the displacement should have the same value. They should be the same number. 115577 or KK. They should be equal to each other. All right, so I'm going to go ahead and I'm going to put the I component and the J component equal to each other. So writing both of those expressions out equal to each other, so equating those two expressions gives us a quadratic that we're going to solve. So I'm just going to rearrange things and put it equal to 0 just to make it a little bit easier to solve. Well, this is the technique we should be using. I'm going to factorize. I'll factorize out 3t. Leaves with 1 minus 0.1t equals 0. And we know from here the two solutions, t equals 0 or t equals 10. T equals 0, well, that was the starting position. It's not really the one that I'm interested in. But t equals 10, that is when it's exactly northeast of the origin. The t equals 0 it was on the origin. Does that count as being northeast? Let's see if the context of the question allows us to have t equals 0 as one of our answers. But for this case, and in this instance, I'll go for t equals 10. Okay, finally, part D. There's a second skater. She has a position vector of 0, 1.1t minus 6. So she's not moving horizontally at all, just moving vertically. And we need to show that these two skaters are going to meet. So letting the context drive the question here. If they're going to meet, what do we know about their variables? We know their position vectors will be the same for a particular value of t. So if they meet, or if they collide, or if they crash, these are the contextual words that mean check when the position vectors are the same. All right, since this second skater has an easy I component, let's put the I components equal to each other. So horizontally, when are they in the same place? And if we solve for t, well, actually, I'm going to tidy this up a bit first. I can multiply through by 10 just to get rid of some of these decimals so I can keep on working by hand. So factorize out the 2t, left with 12 minus t. Two solutions, t equals 0, t equals 12. Okay, I don't know which of these two is the correct answer. I'm not going to discount t equals 0 because maybe they met right at the very beginning and actually never meet again. So I'm going to keep on working, and it should give us some illumination of which of these two is potentially the correct answer. Okay, so let's equate the j components. Once again, it's going to give me a quadratic to work with. And factorizing to solve. Actually, this one's a little bit more complex. We could just use the equation solver on our calculator. I am going to multiply through by 10 first, just give us much nicer numbers to work with. Equation solver on the calculator. I can actually factorize this in my head. But yeah, t equals 5 and t equals 12. Okay? And if we see, for both of these components, they have t equals 12 as a solution. So t equals 12 is the one solution that makes both of these components equal to each other. So t equals 12 is the value we're looking for. These two skaters will meet, will collide, will intercept, will crash when t equals 12. So that's assuming they continue on the paths of motion that they had to begin with.